In this video, I'm going to run through the remaining exercises in 17.1, which is on mass spectrometry. In the first question, you're asked to write an equation to show how nonane is ionized. So you would need to be able to write the molecular formula of nonane. Because it's non, it's got 9 carbons, and because it's an alkane, it's going to follow the general formula CnH2n plus 2. So that's your molecular formula. When it is ionized, it loses an electron. They always lose an electron. So when it loses an electron, it forms a positively charged ion. Now, if you wrote this the other way, if you wrote CnH20 minus an electron goes to this ion, then that's fine. It's just common convention to always have it as plus electron, which is why they bring the electron to the other side of the arrow. In the next question, you're asked about butanol, the same question. So again, you would need to write out the formula for butanol, and then again it is losing an electron, forming a positive ion. If you wrote minus electron there instead, that is fine. The next few questions are straightforward. Question 3, you're just reading the peak of the mass spec that you're provided. In question 4, again you're asked about butanol. They want you to identify the fragment that produces a peak at 29. 29 is a number we've seen before. It's typically C2H5, and in this case that's exactly what it is, C2H5. You're then asked about the fragment with a mass of 31. This one you probably need to work out. So if you look at butanol, draw it out for yourself and then try and find a fragment that would give you a mass of 31. Typically a good place to start is just seeing how many carbons you can put in there. So if you had 2 carbons in the fragment, each with a mass of 12, you'd have a mass of 24, and then you'd have 7 remaining. Now you can't get 7 hydrogens around those 2 carbons, so you know it's not 2 carbons. So your other option, if you've ruled out the fact that it's 2 carbons and it can't be 3, is to look at the OH that you also have in butanol. So oxygen with a mass of 16, hydrogen with a mass of 1, combined they give you a mass of 17. You need another 14 to bring you up to 31, and the OH bond to a CH2 gives you that 14 to give you the right peak. The next question, you are asked about hexane-2-one, and you're told that there is a peak at 43, and you're asked to suggest 2 possible fragments. 43 is an ion that we see all the time, okay? C3H7, written out here in structural formula, but you can also get a mass of 43 from a CH3 group bonded to a C double bond O, and hexane-2-one has both of those possibilities. Again, draw hexane-2-one for yourself. It makes it so much easier once you've got it drawn on the page. Then they ask you to write an equation to show how these fragments would form. So remember, you're starting off with the molecular ion, so you're writing hexane-2-one as an ion. If you don't have that positive charge, you're wrong. And then you're showing that ion breaking down to produce the fragments. So if it were to produce the CH3, CH2, CH2 fragment, then this would be the remaining fragment. And because they want you to show that this is the peak, then you're going to put the positive charge with the C3H7, meaning the other fragment is a radical. Same story for the next one. You're writing this as an ion. It's your molecular ion. It breaks down to form the following 2 fragments. Again, you're interested in the peak at 43, so you're going to put your positive charge with the CH3CO, meaning the rest of the molecule is a radical. So when you break a molecular ion down, you get 1 radical, you get 1 positively charged ion, always positively charged. The start of exercise 3, you're asked to complete this table, so I'm not going to go through all of it, okay? You're told that your starting molecule has a formula mass of 88, and the first peak also has a mass of 88. So this is the molecular ion peak, okay? It's the unfragmented molecule that's managed to make it the whole way through without breaking up. Therefore, you're not losing any mass, so nothing is being lost, and you're just going to write the molecular formula of a fragment. Is just going to be the full molecule written out with a positive charge, okay? Remember, they're always going to be positively charged, and then they draw out the structure. They put the positive charge there next to oxygen. It doesn't matter where you put that positive charge. You could put a big square bracket around the whole molecule and a positive charge, or you could put the positive charge on one of the individual atoms. It doesn't matter where it goes. The next one says that you've got a peak at 59. If you've got a peak of 59, you must have lost 29. Remember, the total mass is 88. 29 and 59 gives you that 88. If you're losing 29, it's typically the C2H5, that's often adds up to 29, but in this particular molecule you've got another option. It could be a CHO, so that's a C double bonded to an oxygen, singly bonded to a hydrogen. Both fragments have the same mass. Because both fragments have the same mass, you've got two possibilities here. This is your molecular formula of one fragment, again with a positive charge. This would be the molecular formula of the other, and then they have it here drawn out in full. Again, doesn't matter where you're putting that positive charge. Next peak has a value of 45, therefore you're losing 43, because 45 and 43 gives you 88. If you're losing 43, well, what could it be? Again, typically when we see 43, it's a C3H7. If you're losing C3H7, then this is what you are left with a positive charge, and they've drawn that out for you here. This time a peak of 43 means you've lost 45. We've just seen the 45 right here. Okay, so this is what you are losing, and this is what's giving you the peak. Okay, so this is a classic example. The molecule is splitting in two. In some cases, the positive charge stays with the carboxyl group and you get this peak. In some cases, the positive charge stays with the alkyl portion and you get this peak. The rest of the table follows the same pattern. The next one then is the exam style questions. So you're asked about methyl propanoate. I would suggest drawing methyl propanoate for yourself. I know we haven't done esters yet, but it just makes it easier to see. And then to attempt answering these questions. So the first one, they just ask you what a molecular ion is. It's the unfragmented molecule with a positive charge. So if you don't mention that it's charged, then you're not explaining why it's an ion. So make sure you're including that. They ask you what you would have lost to have a peak at 71, I think it was. So you find out that you've lost a mass of 15, so therefore you are likely losing a CH3. They said there to ignore the positive charge. They've asked you what you're losing in order to produce this peak. So it's the peak. The fragment that produces the peak has the positive charge. The fragment that's lost, CH3, does not have the positive charge. This isn't what's producing the peak, this is what is lost. So if you did have a positive charge, they gave you the mark, but this is not what's producing the peak. So once you've lost a CH3, what you are left with that's actually producing the peak, that's got the positive charge. If you remove CH3, you are left with C3H5O2 with the positive charge. You do need the positive charge in this case because it's actually producing the peak. And then they ask you to suggest two different structures for this fragment of C3H5O2, and these are the two different fragments. So the first one, if you lose the CH3 from the ester group, the second, if you lose it from the hydrocarbon chain. Sorry, I should really just draw this for you and make it a lot easier. So it's methyl propanoate. Prop tells me, oh, sorry. I don't know if my pen is working. Prop tells you that you've got 3 carbons in the carboxylic acid portion. Oh, wait. Sorry. And then it's methyl propanoate, which means you've got a methyl group in the alcohol portion. And we will do esters, so that will become much easier for you to draw. So what they have here is if you lose the CH3 from the ester group, so if you lose it from there, what you are left with is this. So a CH3, a CH2, a COO, and that would have a positive charge. Or you can lose the CH3 group from the other side, and then this would be the fragment that you are left with, the CH2, the COO, CH3. Okay, so 2 possibilities there. The last question, they ask you to suggest how you end up with a peak at 59. So again, the easiest thing to do here is see what you are losing. If you have a peak at 59, then you are losing something with a mass of 29. So I do 88 minus 59. I see I'm losing something with a mass of 29. 29 is typically a C2H5 group. And if I edit this slightly, I will see that I am able to lose that C2H5 group. So that is plausible. Once I lose the C2H5, I'm left with a COOCH3, which is what they've got here, remembering to put that positive charge. So they have the molecular formula and they also have the structure. When you're giving the formula of fragments, I would typically use structural or skeletal formula. Molecular formula is often not accepted on the mark scheme because it just doesn't give the required level of detail. Then it asks you for the fragment that produces the peak at 87. The entire thing has a mass of 88. If you're only losing a mass of 1, then you must be losing just 1 hydrogen atom. So the molecular formula is just the molecular formula that you started with minus a hydrogen atom, or you can just try pulling a hydrogen atom off pretty much anywhere in the molecule. So they've taken it from that CH3 on one side, and then they've taken it from the CH3 on the other side. But as long as you're losing a hydrogen from someplace, you would get that mark. So the next question, you're asked about empirical formula. So the first part of it should be straightforward. You get the empirical formula and it is C2H5. Then they ask you to use the mass spec to find the molecular formula. So if you look at your mass spec, you'll see that the molecular ion peak is at 58. So that's the highest peak, the peak with the highest mass to represent the unfragmented ion, and it's 58. So the overall molecule has a mass of 58. If we look at the empirical formula that we just calculated in 1a, and we get the relative formula mass of the empirical formula, we'll see the empirical formula has a mass of 29. So if the molecule and the empirical formula don't have the same formula mass, then they are not the same. So what you need to do then is you need to take your 58, divide it by 29, and you get 2. And then you take your empirical formula and you multiply by 2. So I end up with C4H10. Okay, and that's your molecular formula. Then they ask you for the peak labelled X. The peak labelled X has a mass of 43, and it's going to be C3H7, which we have seen a couple of times before. C3H7 at 43. So the next question starts off in the same way, asking you to find the molecular formula. You are given the percentage composition data, so you use this to find the empirical formula. So for carbon, it's 85.71%. I divide that by 12, the formula mass of carbon. I do the same for hydrogen. These are the values I get. To simplify this ratio, I divide both numbers by the smaller of the two numbers. So I simplify my ratio into whole numbers, 1:2. Therefore, my empirical formula is CH2. To find the molecular formula, I then get the formula mass of my empirical formula. Carbon is 12, 2 hydrogens gives me a total formula mass of 14. I'm told in the question that the formula mass of the molecule is 70. So I take the mass of the molecule 70, divide by the formula mass of the empirical formula, 14, and I get the answer of 5. I then take my empirical formula, CH2, multiply by 5, and get the molecular formula, C5H10. So once you have your molecular formula, C5H10, you need to draw 3 possible structures. You are told that it is a straight chain alkene, so all 5 of those carbons must be in a row. First thing I can do is just alternate where I put the double bond. So first of all, I'm going to put it here between carbon 1 and carbon 2, and I've got pent 1-ene. Then I can go between carbon 2 and carbon 3, and I get pent 2-ene. There's no point in moving it anymore because I'm just redrawing the same 2 structures. But you're told that you need to have 3 structures in total. That means you must have a stereoisomer. Okay, so remember, with stereoisomers, your criteria are both carbons of the carbon-carbon double bond must be bonded to 2 different groups. The first carbon here of pent 1-ene is bonded to 2 hydrogens, therefore I cannot draw stereoisomers of pent 1-ene. But if I look at pent 2-ene, carbon 1 is bonded to a hydrogen and a CH3, carbon 3 is bonded to a hydrogen and a C2H5. So each carbon of that double bond is bonded to 2 different groups. That means I do have stereoisomers. So what's shown here is E, pent 2-ene, and then here you've got Z, pent 2-ene. So in Z, pent 2-ene, the 2 high priority groups are on the same side of the double bond, and in E, the 2 high priority groups, the CH3 and the C2H5, are on opposite sides of that double bond. So they are your structures. And then it asks to use the fragment data to decide which structure is correct. You're told that there is a fragment with a mass of 28, which is from the C2H3. So, a fragment of 27. So 2 carbons will give you a mass of 24, and there's room for 3 hydrogens. So in order to work that out, you've only got carbon and hydrogen. If the total mass is 27, you only have 2 carbons in there. If you have 3 carbons, you'd have at least 36. So you only have 2 carbons in there. That accounts for 24. The other 3 must come for 3 hydrogens. So then you need to look through your structures and see which one will give you C2H3. So 2 carbons and 3 hydrogens. So this here, you can see this fragment. This carbon here is bonded to 2 hydrogens, whereas this carbon here is just bonded to 1. So by breaking this single bond, I'm left with a fragment C2H3. Because it's the fragment producing the peak, I'm giving it a positive charge, and I can only get this fragment from pent 1-ene. I can't get it from the other 2, meaning it must be pent 1-ene. Okay, the last question now. You are given the mass spec of an unidentified molecule, and you're asked for the molecular mass. In order to get this answer, 72, you just look at the spec and you go to the highest possible peak. So your unfragmented molecule gives you the highest possible peak, and it's at 72. Okay, now I know the mass of my molecule, 72, and I'm told that this molecule contains carbon and hydrogen only. So if I know it's got a total mass of 72, and I know it only contains carbon and hydrogen, I'm able to figure out what the molecular formula actually is. And I do that by dividing by 12. Carbon has a mass of 12. If I divide by 12, I see how many carbons I can get in there. Okay, so 5 12s are 60, 6 12s are 72. But I can't just have 6 carbons by themselves. So the maximum number of carbons I have, the maximum number of carbons I can have is 5. So 5 carbons max, and that leaves 12 left over for hydrogens. Okay, yes, you can get 6 carbons because 6 12s are 72, but it's not just going to be a molecule with carbon alone. You need room for hydrogen. That means you've got 5 carbons and 12 hydrogens. If you had less, if you had only 4 carbons, so 4 carbons would give you a mass of 48. And then you'd have way too many hydrogens that wouldn't be able to fit around just 4 carbons. So it has to be C5H12. And once you know it's C5H12, you're then asked to draw out the different structural isomers of C5H12. So the first one, you put all of your carbons in a chain. The next one, you would put just 4 carbons and you'd have a branch, so 2-methylbutane. It doesn't matter where you're putting that branch, it's still 2-methylbutane. And then you would draw 3 carbons and you would have 2 branches on the same carbon, and that would be 2,2-dimethylpropane. Now, it did ask you for displayed, and I was lazy and drew skeletal. Okay, if you're asked for displayed, you do need to draw out all of the atoms and all of the bonds. I know that's a pain, but that's what you should have drawn, not what I did. And then you were asked to identify the different fragments. So you were told one that has a mass of 15. We've seen that lots of times. It's a CH3. Make sure you've got that positive charge. Then you were asked for one that had a mass of 43. So that's there at the bottom, CH3, CH3, CH2, again with a positive charge. And that middle one there, a mass of 57. So again, that's if you've just removed one CH3. They should all have a positive charge. It says here at the end, in each case, award only 1 mark if only simple formula. So this is what I'm talking about, where they don't want you to use molecular formula. They do want you to actually show the structures involved. So make sure that you're doing that. Whether you're doing skeletal or you're doing structural, don't just do molecular formula.